Hi, welcome to this lesson on probability. In the first lesson of this course in statistics, you learned about various times when probability plays a role in your life. Think back to the latest board game, where you needed to roll that 6 to win the game, or how you went to work and during your commute all the lights were green. What are the odds of that happening? Probability also plays a role for HR. Think for instance about turnover. What's the probability that a certain employee will leave in the next 12 months? These are interesting questions, and by calculating the probability, you can answer them. So, let's get started. Let me begin with a delicious example. Let's say you're working for a small to medium-sized company, and your manager wants you to boost engagement of the company by having a lottery every day. Every day, 1 out of the 5 departments will receive a free lunch. In this example, every department is similarly sized, and having a free lunch does not impact your odds of getting another free lunch at a later date. Knowing this, that means that there is a 20% chance each day a certain department gets a free lunch. So let's say you're in the sales department and you want to know what the chances are of you winning a free lunch. You can calculate this by dividing 100%, as one of the departments will receive a free lunch, by 5, as there are 5 departments, which is a 20% chance that you will win. In terms of statistics, we write this down as follows. P sales equals 0.2. P stands for probability and always ranges from 0 to 1. In order to turn the p-value into a percentage chance, you simply have to multiply it by 100. In our case, 0.2 times 100 is a 20% chance. Now this may sound easy, but trust me, you need to understand this so we can build upon this foundation. Back to the free lunch. Winning the lunch is mutually exclusive. There can be only one winning department per day after all. This will allow us to use the simplified addition rule, which says that the probability of sales or HR winning the lunch is the sum of the chance HR or sales will win. We write this down as follows. P sales or HR equals P sales plus P HR. In our case, this is P sales or HR equals 0.2 plus 0.2 equals 0.4. Now let's add something extra to this lottery. Let's say the manager wants to give departments a 10% chance to win a free cake, independent of the 20% probability of winning a free lunch. Both lotteries are not mutually exclusive, meaning you can win both, one of them, or none. The odds of getting a free cake don't change on the probability of winning a free lunch. Now we can calculate this further. What's the chance of getting the best day ever at work in the sales department, namely a free cake and a free lunch? For this, we multiply the odds of getting both free cake and a free lunch. Thus, we write down P lunch and cake equals P lunch multiplied by P cake equals 0.2 multiplied by 0.1 is 0.02, which is a 2% chance. But what if you're on a diet and don't want to receive both lunch and cake, but you are interested in one of them? Do you still count them up like we did previously, namely P lunch or cake equals 0.2 plus 0.1 equals 0.3? You don't, because you need to subtract the possibility of getting both from this equation, as they are not mutually exclusive. So you get P, lunch or cake, equals 0.2 plus 0.1 minus 0.02, which equals 0.28. So far, so good, right? Just remember that OR means adding and means multiply. Now, what happens if the probability of event A depends on event B? For this, we look at conditional probability. Conditional probability is a measure of the probability of an event occurring given that another event has occurred. The conditional probability of A given B is usually written as PA over B. If A and B are independent of each other, P A over B is the same as PA, as the effect of event B has no effect on event A. However, if they are not independent of each other, we calculate PA over B by taking PA and B divided by PB. Now let's turn this into a more concrete example of HR. Turnover. What are the odds of someone leaving given that his engagement score is low, for instance. That's a classic example of conditional probability. For this, we can take P leaving over low engagement score is P leaving and low engagement score divided by P low engagement score. Now what if you created a turnover test, where you not only included engagement, but also other turnover indicators, such as commute distance, tenure, family status, and more? You've standardized all these factors and are now able to predict turnover. Brilliant, right? Every time someone scores above 15 on your test, the test will come back positive and say that the person is likely to leave in the next 12 months. But you want to see how well your test is performing. What are the chances given that someone leaves when your turnover test says that that person will leave in the next 12 months? For this, we can make a 2x2 roster. At the top, you will find whether they left or not, and at the left, you will find their test results. So when your test says yes, and the person actually leaves, that means your test gave a true positive. Similarly, if your test said no and the person didn't leave, your test gave a true negative, which is on the bottom right. In a perfect world, we would only have true positives and true negatives. However, people are not always as predictable as statisticians would like them to be. Therefore, they often fall into the top right and bottom left, the false positives and false negatives. A false positive is when your test said that the person would leave, but they actually didn't. A false negative is when your test said that the person wouldn't leave, but the person did in fact leave. This is a huge problem for many areas that handle statistics, mainly in medicine, but also HR. Getting a false positive might mean that your manager will stop giving you promotions or challenging assignments, as they assume that you're going to leave anyway. Getting a false negative will cost the company a lot of money, as a person is leaving out of the blue, often not easily replaced by the company. To look into this more closely, we look at accuracy, precision, sensitivity, and specificity. Starting off with the most important one for organizational research, accuracy. Accuracy looks at the number of correctly identified individuals versus the number of incorrectly identified individuals. In statistical terms, you take the sum of true positives and true negatives and divide it by the entire sample, or in statistical terms, true positives, true negatives, false negatives, and false positives. In predictive algorithms, accuracy is the most important measurement to determine the success of the algorithm. In an ideal world, our accuracy would be 100%. But unfortunately, the real world is often not as predictable as we would like it to be. Next, sensitivity. Sensitivity, or true positive rate, looks at the test's ability to correctly identify people who want to leave. To do this, you look at the number of true positives and divide this by the sum of the true positives and false positives. Or in our turnover case, you look at the number of people who left the company and were diagnosed by the test as a turnover risk, divided by the sum of people who left the company and the people who were falsely identified as wanting to leave the company. Specificity, or true negative rate, looks at the test's ability to correctly identify people who won't be leaving the company. To put this into practice, let's say you test this out over 1 year in your company with 1,000 employees. Your threshold is that people who scored over 15 on your turnover test would be labeled as a turnover risk. Of this, the following diagram emerges. 50 people ended up leaving the company, of which the test was able to predict 40 of, and 10 received a negative test. There are 950 people who did not leave the company, of which 150 people had a positive test, and 800 people had a negative test. Our accuracy, in this case, is 40 plus 800 divided by 40 plus 10 plus 150 plus 800, which equals 84%. So 84% of the time, the test was accurate in its predictions. This means that our sensitivity is 40 divided by 40 plus 10, or 80%. This means that 80% of the time, your test was able to accurately predict when someone actually wanted to leave the company and received a positive test. Our specificity in this example is 800 divided by 800 plus 150, which equals 84%. Also not bad. Or is it? Well, that depends on what you want to get out of the test. Is your company on the cutting edge and you want to minimize the chances of someone leaving, so you want to be able to more accurately predict whether someone is at risk of leaving? Then it might be a good idea to up your sensitivity by lowering your threshold of 15 to 12 in your turnover test. This could give you the following diagram. Here, you can see that we're incredibly sensitive to turnover with a 98% sensitivity. However, due to the lowering of our threshold, we also get a lot more people who are false positives, which decreases our specificity to 53%. This means that in general, your accuracy will also go down to 55%. This is what your data scientist will look for, and he won't be too happy to see that the test's accuracy has gone down. Similarly, if you want to increase your specificity, sensitivity has to go down. These changes are always a two-way street. You have to keep this in mind when selecting a threshold for your tests. Now let's go to another example, where HR has designed a turnover test with 81% sensitivity and 86% specificity, better than our original example. This company, however, has 100,000 employees. Now, what is the chance that an employee gets a positive result on the turnover test and actually wants to go? Or in other words, P leaving over positive test equals P leaving and positive test divided by P positive test. Take a few seconds and try to see if you can calculate this on your own. In a few seconds I will give the answer, so pause the video now if you want to calculate this on your own. If we put in the numbers, we get that 810 people have a positive test result and wanted to leave, but 14,670 people received a positive test result. This means that when we find a person with a positive test result, there's only a 6% chance that they actually want to leave the company. If you have a similar test, you may want to reconsider putting this in place. These mistakes may end up negating the positive effect of implementing such a test, as the risk of misidentifying a person and its associated consequences, which is less chance of promotion, worry about finding a replacement, is too much. Besides accuracy, sensitivity and specificity, precision is also an important aspect of a measurement system. Precision of a measurement system, related to reproducibility and repeatability, is the degree to which repeated measurements under unchanged conditions show the same results. A good way of looking at accuracy and precision is that bias, from the previous lesson, is the amount of inaccuracy, whereas variability is the amount of imprecision. The more precise your test, the better you will repeatedly get the same type of results. Here's a picture that illustrates how precision and accuracy work together. Each shot is a sample, and what you want to measure is represented as the bullseye. At the top left, you see a target that has low accuracy and low precision. Their test results are all over the place. The top right one has low accuracy but high precision. Here, they are clearly missing the bullseye, but their outcome is very precise. Whenever they collect a sample, its variability or spread is very low. Now the bottom left has a lot more variability, but at least it's closer to the target and thus has a high accuracy. The bottom right is what you really want. Both high accuracy and high precision. You measure exactly what you want to measure every time. This picture illustrates how accuracy and precision are intertwined. To sum up, now you know what probability is, how you can calculate it, and how tests are calculated in terms of accuracy, sensitivity, and specificity. Finally, I briefly talked about precision. In the next lesson, I will be talking about hypotheses and statistical testing. Probability has a large role in this, as nothing in statistics or HR has a 100% definitive answer. We always work with a certain amount of probability. I hope this lesson has given you more insights into this aspect of statistics, and I'll see you in the next lesson.